Yes, welcome to Easy Gates Gate 22 Instrumentation Solutions, and this is based on the response sheet, and the question number is given as per the master question paper. Okay, so you can refer the master question paper, question number 47, for a perfect answer. A problem from analog electronics. So we have a NMOS circuit given, and no DC biasing given. Problem is straight away for the AC small signal voltage gain. Okay, so let me read the statement. In the small signal circuit shown, the N-channel MOSFET is biased in saturation with the transconductance GM. Okay, then small signal low frequency voltage VD is injected at the supply terminal, that is resulting in a small signal voltage fluctuation V0 at the output terminal. If we ignore the channel length modulation of the MOSFET, then the small signal voltage gain V0 by V in is. That's a problem. So you can take conveniently, let me take this point as the AC small signal source. We are injecting V in, and this is my output V0. Then I need to replace this NMOS by its small signal equivalent, and hope you are familiar with the NMOS small signal equivalent. The NMOS small signal equivalent is going to have the transconductance parameter GM, but I prefer to play with small RS instead of GM. So let me use small RS. This is your drain, this is your source, and this is your gate terminal. And not to forget that small RS is equal to 1 by the transconductance. And this voltage difference is equal to 0 as per the small signal equivalent. Now let us begin the small signal AC analysis. So I'm taking the problem straight away forward. Voltage gain. So effect of V in on V0, the goal is to find V0 by V in. Small signal voltage gain V0 by V in. 4 options are given. Okay. So once you deduce the answer, then try to match with the given option. That's a better route. Yes, this is the small signal equivalent circuit, the supply voltage V in and the response V0. Okay. So then remember, as per the small signal AC equivalent, this potential difference is 0. Since this potential is given as V0, instead of playing for a nodal analysis, let me play like this. So this is V0 means, so no current in the gate terminal. Therefore, the voltage V0 will be shared between this R0 and this R0. So it is going to become V0 by 2. If that is the case, this point is also going to be V0 by 2. Then the current is going to be V0 by 2 times small rs, because the V0 by 2 is going to fall across this small rs. Assuming V0 is positive, so V0 by R2 will be positive, current will be down. That's your channel current during the AC analysis. The same channel current will be figured here, ID. And since no gate current and current is only through the capital R0 and capital R0, the current here will be V0 divided by 2 times your capital R0. Okay, and that's a total current existing here. The total current existing here will be V0 divided by 2 R0. You got to be a bit careful because there are 2 currents coming into the play. So V0 by 2 R0 plus V0 divided by 2 times small rs. V0 by 2 times small rs. That's what we are getting. Fine then. So then what we are getting is, then we are going to lose a drop I into capital R0 across this from V. So therefore, the V0 is going to become the supply voltage minus the drop, that is small signal drop across this R0. Okay. Yes, that's all. You will get your solution now. So V0 is equal to, what is that? V in minus, what is your current? V0 by 2 times R0 plus V0 by 2 times small rs into your resistance capital R0. That's all. Simplify this equation. So if you rearrange, anyway, the capital R0 is figuring in your gain. So therefore, you can get the response as a function of your small rs, that is in terms of GM and capital R0 as expected by the designer. Okay, so multiply R0, you'll get the resultant as V0 is equal to V in minus V0 by 2. Let me take what is the remaining. If I take V0 by 2 common, what is the remaining? V0 by 2 common means then multiply by R0, you will get 1. 1 plus R0 by RS, you will get 1 plus R0 by small rs, you will get. So we are looking for V0 by V in. So that's a voltage gain of this amplifier. So then let me take the entire V0 to one side. So it's going to become V0 plus V0 by 2 times 1 plus. Let me write this as GM into R naught now. Okay, so 1 plus R naught by RS GM into capital R naught. Okay, because small rs is equal to 1 by GM. Time to replace RS by its transconductance of the N mass given. Okay, that is equal to the supply voltage V. Okay, so then it's very easy. So V naught, then taken common. So 1 plus, so V naught is taken. So it's going to be 1 by 2 plus into 1. So plus GM into R naught by 2 you will get, that is equal to V. So what is the resultant? This is going to become 3 by 2. So therefore it is V naught. Okay, so into 3 by 2 plus GM into R naught by 2 you will get. So that is equal to V in. So then from this V naught by V in is equal to, what do you get? So the 1 divided by the whole thing, it is going to be 3 by 2 plus GM into R naught divided by 2. So depending on how the options are given, we'll modify this expression. Anyway, that's a voltage gain. So it's 1.5 plus GM, 1.5 plus 0.5 GM into R naught. Okay. So let me check what is given in the options. So we need to compare our result with what is given. Okay. So this is our result, V naught by V in. Okay. So a quick check. So we can, yes, V naught by V in, we can write, yes, V naught by V in, we can write as, it's given inverse. Okay. Inverse means what we get. 3 by 2, what we get actually 1 by 3 by 2 plus GM into R naught by 2. So that means if you go for the inverse, it is going to become 3 by 2 plus GM into R naught by 2, the whole inverse. Yes. Yes, you know the right choice now. So GM into R naught by 2, yes, plus 3 by 2. So the best possible answer is option D. Yes, that's a very interesting problem using NMOS from analog electronics. Okay. And hope you enjoyed the content delivered, and do subscribe our channel. We'll update you with next problem. Thank you.